Thank you very much. It's a great honor to have the opportunity to speak to you. You know, before I start my talk, which is going to be, I have to see if I use this. Okay. Before I begin my talk about how I see the future of the computing industry and a brief history of what Xilinx has done since its inception back in '85, and the role that we see that will play in this new era of computing. Simon asked me to share a little bit about myself personally, but I didn't prepare any slides, so I'm just going to do this a little bit ad hoc. You see, and you hear me speak, and clearly I'm a Chinese American, but very, I guess, capital A American. But I was born in Taipei, but my family emigrated before I was 1 year old, so I hadn't done the ceremony where I called yet to find the thing. I was only 9 months old. I lived in New York City, in Queens, this is back in the 1960s, and my parents were both graduates of NTU. But back in the 1960s, American companies did not recognize their degree at all. So I would say that we had very modest beginnings. You know, economically, wasn't necessarily the easiest thing, but we were a very close family. And like many of us, I'm sure, my parents taught us how important education was. And it taught us that, you know, to set goals. And I think because some of the struggles that they experienced, including, of course, prejudice and other kinds of challenges, to a degree, it's sort of the reason why I don't really speak Mandarin, right? My father felt that he didn't want his children to experience some of the things that they experienced, so they wanted us to assimilate. And one of the really nice things I feel is that now today, the fact that I don't speak Mandarin is not good from a business perspective. That it would be actually much better if I could speak Mandarin, and I view that as a great progress of society as a whole. Not to say that we're at all where we need to be, because there's still, unfortunately, a lot of biases, not just against Chinese Americans, but others. But nonetheless, I think that it is progress that now, it's quite an unfortunate thing that I only speak English. As far as professionally goes, I started out my career in 1982 doing chip design. I worked at a company that doesn't exist anymore, Digital Equipment Corporation. And I designed processors for VAX, alphas, alpha chipsets. I came out to California in '97 to work for Silicon Graphics in the MIPS division. And then I became vice president of engineering when MIPS was spun out of Silicon Graphics as an IP company. So I learned a bit about the IP industry. Simon and I both worked together at the one and only startup I was ever in, the T0, ultra-wideband chipset, but I was only there briefly. And then I went to ATI to do GPUs. Of course, ATI got purchased by AMD, and after that I joined Xilinx. I've been at Xilinx for about 10 years now. It'll be 10 years in April. And if I look back on that career so far, 35 years and hopefully a few more to go, I consider myself very fortunate to have worked on some really great products, microprocessors, GPUs, FPGAs, and some of the new technologies I'm going to share with you a bit in a moment. And I'd say, in addition to the incredible amounts of learning and innovation, and having the opportunity to put my small contribution in some of these great products, at least as memorable are the people and the truly brilliant and talented people that I work with. Many Chinese Americans, but not just Chinese Americans or Chinese engineers. But I think it is both the technology and remembering the people. Those are things that last with you. And I'm a newly minted CEO. I became CEO, the fourth CEO of Xilinx at the end of January. So again, I guess this analogy of I'm a baby CEO, right? Just trying to get through my first year. But it does make me reflect that I do believe that you should remember where you came from. So I think a really important thing for a CEO is to, treat their employees with the kind of respect, help them be successful, help them grow and develop. of course, be dedicated to your customers, and also, deliver for your shareholders, the owners of the company. So I endeavor to try and do all those things, as well as continue to produce really exciting and breakthrough products. I mean, I'm the CEO, I'm not just doing engineering anymore, but I'll always have a passion for products. So with that, I guess I'll give you a little bit more of a history about Xilinx, in case you're not familiar with it. Oh, wrong way. Okay, so Xilinx invented the field programmable Gatorade Fpga back in '85. It was in 2.5 micron technology, or for people who are a little bit younger, that's 2,500 nanometers. So, when you think about it that way, it's pretty extraordinary how many orders of magnitude change there's been. It had 64 logic cells, right? This is a very flexible Gatorade where you can implement, it's an amazing thing, right? You can implement any kind of logic flexibly without having to do a chip tape out. It had 58 I/O blocks, and it's probably, I don't even know what the standard was. I'm sure it was just bang bang digital kind of I/O. So to give you, I apologize, to give you an idea of like a more recent product we put out, this is 16 nanometer FinFET technology, right? So 16 nanometers as opposed to 2,500 nanometers. It was introduced actually at this point, 2015, but it's still state of the art. It has 1.1 million logic cells, so 4 orders of magnitude increase in capacity from that perspective. It has 930 I/O blocks, but that includes very high-speed SerDes, which we have our chief SerDes architect here. And it also has a complete SoC. So this block diagram is the SoC that's contained within all of that. Quad A53s, dual R5s, it's got a GPU. Some of these things have integrated video codecs. A very complete peripheral bus. So this is an incredibly powerful and very complex product. And that gives you an idea of how far things have evolved from our beginnings of creating this new product category. Okay. So Xilinx, in the early days, Xilinx actually had the greatest traction in the communications market, right? So this is wired and wireless communications. And if you recall, unfortunately, this is an incredible thing. Internet 1.0 happened, and right around 2000, though, we kind of had the internet bubble burst. And the entire semiconductor industry, in fact, went into a major recession that lasted years. And Xilinx's revenue at that point in time, I believe, was around 80% in communications. And the revenue dropped, I think, like about half or something, very close to that, in like 1 year. And the company rapidly diversified and covered all these other markets now. So when I joined Xilinx in 2008, it was already many years that had been fully diversified. At the time, I think communications was maybe about 50% of the business. Now today, communications is around 40% of the business, plus or minus a few percent. And as you can see, there's some really great market segments. Sorry, eventually I'll figure this out. Such as automotive, right? We're in all kinds of industrial applications. We're, of course, continue to be very strong in communications, both wired and wireless. We're in drones, we're in robotics, we're in AR and VR headsets. So this is a testament to the breadth and the flexibility and adaptability of the technology and the products that we produce. And these will always continue to be very important markets for us. But more recently, as in, I'd say, the last year and a half, though a very interesting thing has occurred is where you see a tremendous amount of growth opportunity for us within the data center. And I'm going to talk about the underlying trends of why I believe that's happening. And it's just the very early days of that happening. I will also point out that typically today, when people talk about the data center, most people focus on computing, right? So processors and now GPUs, because there's a lot of NVIDIA's success recently with machine learning training. But again, because our platform is so adaptable and flexible, we play not only in compute acceleration, but we also can create tremendous value in storage applications as well as on the network side. So to give you an idea of some of the breadth, this is a very small subset of some of the things that we could accomplish in terms of acceleration in the compute acceleration side. So for brevity, I'm not going to talk about storage and the networking side. And these numbers are factors of performance improvement versus Intel Xeon, server class processors that you find in cloud, public or private clouds. And these factors are also things that were achieved by Xilinx partners, in other words, application developers that are targeting FPGA card. What you see there is a very standard PCIe kind of acceleration card. It could look like just like what a GPU card is. But inside, of course, what's being accelerated is acceleration on FPGA. So things like machine learning, 40x performance relative to a CPU. By the way, that's performance, but from a performance per watt, we have similar kinds of significant improvements. I should also say that this is machine learning. We tend to focus on inference, although there's no first principle reason why we actually couldn't do training, but especially training typically is in embedded applications. But I'd say there's a lot of research on how we could also accelerate training. But this is inference. But we're not just focused on machine learning. Obviously, that's a very big, multiple industry trend. We could still accelerate a lot of the other applications that are driving compute needs and also driving all the bandwidth requirements and communications infrastructure. So video processing, so video transcoding, everybody, a lot of people are taking pictures or videos, so there's video streams coming in from different size screens, and it's got to be streamed back out to different size screens. So video transcoding we can accelerate by a factor of 10. Data analytics, such as search, image, even video analytics, we could accelerate that. Each of these, again, are different companies. And the last one is genomics. I should mention that the companies, I don't mention the companies here in the slides, but these companies are participating in Amazon's FPGA as a service platform. I don't know if people are aware of that, but about a year ago, Amazon enabled FPGAs in the cloud. So people could develop applications targeting FPGA accelerator, and then of course users can buy those applications in the Amazon marketplace, and then rent time, right, on a GPU accelerator card or a number of these cards. And all of these companies that achieve these factors are part of the Amazon marketplace. So this just gives you a brief feel for some of the things that we can do in today's technology. And this is generally, these are data points we're generally running on 16 nanometer technologies, as I shared with you. The other thing that's different is for most of Xilinx's history, our customers are really FPGA designers, which is a subset of chip designers. But a lot of the innovations happening in the industry today, of course, is in software. And although I'm a double E, and I imagine many people here are double E's, today a lot of the young people are going to computer science, applied mathematics, statistics, and so forth. So one of the big shifts Xilinx is doing is we're enabling software developers. And we've delivered the entire software stack to industry standard open frameworks like Caffe, TensorFlow, and so on. Even where there isn't such standard frameworks, we also allow people to now program our products using C, C++, or OpenCL. And we, working with other third parties as well as ourselves, put out optimized libraries for different domains. Now, underneath the hood, we're still going through the entire process of taking those various description languages, synthesizing them to RTL, doing place and route, time enclosure, all those things. So basically creating custom silicon underneath the hood. But what we're going to do is we're going to enable software developers to get the power of a customized silicon accelerator without having to know anything about doing silicon design, right? And I think that really is, which I'll explain in a moment, I think going to be a very important part of the next era of computing, which is exactly what I'll talk about next. So, if you look at mainframe era, this is like the 60s, 70s, and part of the 80s. And I actually somewhat, when I started my career, again, in microprocessors, right, it's like we all really knew that us microprocessor designers, all we were doing was stealing all the ideas from the mainframe designers and integrating into, first chipsets and eventually a single microprocessor. Right? I mean, a lot of the techniques that were being done in terms of prediction, speculation, all these things were done in mainframes. Not to say that there weren't other innovations when we kind of went into the 80s and 90s, when the PC industry kind of, became the next era of computing. But much of it really was leveraging architecture that was done in the mainframe world. Even to this day, right, a lot of supercomputer architectures were done actually in the 50s and 60s. So PC industry, that's about when I started my career. Digital is mini computers. That's a computing format that kind of went away, but and PC, really dominated. Still is a very, very significant era, and that's where computing is CPU centric, right? And the next era is mobile, and this is where look, anytime you do these generalizations, you can poke holes in it, but in broad sweeping terms, I would sort of say in the mobile world, really ushered in SoCs, applications processors, a lot of different cores, a lot of different kinds of capability, certainly because of the fact that you have severe power, cost, size, weight kind of constraints that drove certain innovations in those SoCs. And there's still formats that kind of blur between it, laptops, tablets, and whatnot, but basically that era we're still kind of in that era, although it's, I think it's actually starting to trail off. Excuse me. So I say the new era that we're going into is an era where the architectures it's a heterogeneous architecture. So obviously it's no longer CPU centric, it's no longer even SoC centric. It's really going to have a heterogeneous different types of engines for different types of workloads. And that's because the industry's talked about the world as being smart and connected for decades, but we truly are building that world now, right? We are in the early stages, but we are truly building an intelligent, fully connected world. And you can see that, it's like smart homes, smart cars, factories, of course connected through both wired and wireless interfaces going into cloud. So it's a world of pervasive intelligence. So, I'll talk a little about the trends and why that's happening. Is that, what would be a talk that talks a little about semiconductors if you didn't touch on Moore's Law? But this is only one of the trends that I think is driving towards the need for heterogeneous architectures. There's several things that you see here, right? You start from the 70s, where again that was the mainframe era. It's the 80s where the PC era, which is really when microprocessors really came into their own, right? Before it was multi-chips. When microprocessors came into their own in the 80s and went really strong through the 90s and the beginning of 2000, before you start seeing the saturation, you can see that, if you measure by performance, if you single-thread performance, you look at frequency, you look at the integration, power, and everything. This is when Moore's Law was alive and well, and there was a lot of architectural innovation where you could get instruction-level parallelism. That ran out of gas, and then you start seeing in the 2000s, people started putting down cores, started having to go for threaded parallelism, but things have saturated. Right? So things have saturated because we've hit the frequency wall, we've hit the power wall, we've hit the instruction level parallelism wall. So this form of computing is clearly leveling off. And that's simply not going to match the need because of these other trends. Right? So the first trend we all know, and we talked about big data. I will say that even though this has been talked about for at least 4 or 5 years, we're still in the early phases of big data, right? So I've heard statistics like 90% of all the data in the world, right, from the beginning of time, 90% of it was created only in the last 2 years. And most of that, of course, is video and images, and everyone here can create, right, probably petabytes of data, like just tonight. I mean, easily, right? If we just all started shooting video, and as our phones go to 2K, 4K, 2K, and 8K. It goes even higher. So this data is just exploding, and there's more sensors, cheaper forms of sensors. So, mechanical sensors, thermal sensors, all kinds of sensors. That's going to add to this torrent of data. And all this data is very unstructured, right? So just when CPU kind of performance, for all those reasons, have saturated and leveled off, what's happening is there's actually a greater demand for processing the data, more so than when Moore's Law was even working. Like, it's going up, truly exponentially. And so the type of computing that's needed for the future is more of a throughput computing. And yet at the same time, you still have latency constraints. Because just as an example, there's a ton of data being generated and analyzed in the cloud. And as we all know, you actually like to be able to get information extracted out of that data and extract that information very rapidly, because there are certain applications that it's not a batch sort of thing. You really care about how quickly you could take data and generate information and generate value. An easy one to point out is things like fraud detection. If you're watching all these volume patterns, you want to detect fraud very rapidly. So you need throughput computing at the same time you care about latency. High-frequency trading. There's a lot of things where you really care about latency, and yet there's huge throughput demands. The next trend, of course, everybody reads about this. I'm sure many of us are participating in products and development towards artificial intelligence. This really is, again, the very early days, so dawn is appropriate. It's very early for artificial intelligence. It truly is going to be adapted across multiple industries. Of course, many applications. It really will be disruptive. One of the things I point out is, though, that artificial intelligence isn't an application in and of itself, right? It's really a technology, and what's happening is applications are becoming much more intelligent by integrating often machine learning, but not only machine learning, maybe other forms of AI. And the other point is that this is happening, again, often you would think about it in the cloud, where there's public or private, but really this is happening end to end. There's a lot of discussion around endpoint, edge computing, and cloud computing. I tend to think of the 3 levels of hierarchy, so I tend to think of it as an endpoint to an edge and then into the cloud. To give you an example of what I mean by an endpoint is, like, if you have a smart city, right, you have cameras. So a single camera is an endpoint, right, and it's generating a lot of data real time. If, let's say it's a camera that's controlling a traffic or an intersection, there is a real-time latency for it to control that traffic light. It's not going to go up into the cloud, and certainly not going to take that raw video stream and pump it all the way to the cloud. So what happens is you have to do some things locally, and then you create metadata, and then you ship that maybe to some edge point, aggregation point, and then maybe goes into something like the citywide, control room that's trying to optimize traffic flow across the whole city. So that gives you, an example of how I think of it. And machine learning is really going to be at every single one of those points, right? And indeed, when you get into the cloud, you're getting into communications infrastructure, and machine learning is going to be adapted into networks right there. The carriers are already looking at optimizing at the network scale flows to try and get efficiency out of it. They just can't do it by just having raw, over-provisioning of bandwidth, because we're running out of that. Okay. So, okay, the slide got a little bit torqued, but we talked about this already a little bit. I set it up in terms of showing the slide of saturation of the power, frequency, and instruction level parallelism. So basically, the kind of computing, so say CPU-centric computing is maxed out, it's saturated, there's an explosion of data, it's growing exponentially, we have to process it, we need throughput and latency. So it's going to be a heterogeneous kind of systems in the future with accelerators. And because of the breadth of applications, even if you look at machine learning, which is a subset of artificial intelligence, there's many different forms of machine learning. It's not just one. So there's going to be a breadth of architectures. It's not a canonical acceleration architecture like that became a canonical architecture for PC kind of platform, right? And finally, even if Moore's Law were working, the speed at which people are innovating, the speed at which people want to deploy new services is accelerating much faster than silicon design cycles. So for all this reason, we at Xilinx feel like what we've always been doing, which is a form of very, very flexible and adaptable products and technology, is that is increasing in value, because when you build an intelligent and fully connected world, that has to be adaptable, right? And the analogy I use is the species that flourish and sustain over time in nature is a species that's very adaptable, right? And it's because things will change in the environment. And if you're building infrastructure at the city scale or at the world scale, you certainly cannot predict all of the requirements that's going to be needed. And you can't keep changing out that infrastructure. That's economically and just logistically not possible. So while the world is smart and connected, we believe that the thing you have to add to it is it must be a very adaptable, smart, connected world. So, I talked about in the beginning just showing you our first FPGA to 16 nanometers. This is showing some other major milestones that we at Xilinx have accomplished. We invented the first FPGA, then there was a fairly big breakthrough in the architecture of FPGA, the first Vertex architecture. The Vertex 2 Pro is, this is getting into maybe minutia, but that was the first time we put a CPU into this very programmable fabric. That was a Power PC. Truthfully, it wasn't an SoC, it was just a CPU with a little bit of peripheral logic. So, while it found its uses, it didn't really proliferate because there was still not enough around, it wasn't a full SoC, so it kind of required too many other, all those other peripherals needed to be implemented. Now in 28 nanometers, that's when we had a number of really big breakthroughs. One of it we did introduce the first Zynq product, and that's where we integrated a true full SoC, ARM SoC, dual Cortex A9s with first, second level caches, local memory, complete peripheral buses, lots of different interfaces. So we did that breakthrough product. The other thing that we did, which I won't talk too much about, but we also introduced the industry's first 2.5D, we talked about it in terms of 3D FPGA, and this is where we work together with TSMC on their CoWoS technology. So this is the silicon interposer where you can integrate multiple active die connected to a silicon interposer. We did that back in the 28 nanometer generation, and we were the only company that were producing production shipping products with CoWoS for many, many years. Only just recently with GPUs and communications processors, other people adopted the CoWoS technology. So in 16 nanometers, we've gone and introduced our second generation SoC products, the MP SoC that has the quad A53s, the dual R5s. More recently, we also introduced RF SoC, which on top of all that integration, we integrated ADCs and DACs for 5G, so really advanced ADCs and DACs, all on a digital process. And the reason why I share this with you is because we've also been going through this evolution of adding intelligence, adding heterogeneity, if you will, multi-core heterogeneous systems, and we've been doing other forms of integration beyond just monolithic integration, again, CoWoS being one of them. And what we just announced early this week is the very beginning of what we consider a whole new product category, and our 7 nanometer program, which is going to be the first instance of that product category. So we'll be taping that out this year, and next year we'll be shipping it to customers. Maybe I won't figure this out. So what we call this product category, Adaptive Compute Acceleration Platform, or ACAP for short. And this is a product category which is extremely adaptable. You can program it with software. It's still hardware programmed underneath the hood, if you will, and it can really then accelerate a very, very broad range of applications. And I say dynamically because it's not that you could just do this at boot up time, but you could do this while it's actually operating. This just gives you just a sampling of some of the different workloads and applications that we can accelerate this program. And again, machine learning, it will greatly accelerate, and in our view, the machine learning as a technology will be adapted in a lot of these other applications. This is my last slide, just to show you a high-level block diagram of what the first instance of an ACAP is. This is being done at TSMC's 7 nanometer FinFET Plus technology. The code name is Everest. We started this program in advanced development 4 years ago. We've invested over $1 billion, and this will be, you can see the multiple processors, application processors, real-time processors, next generation programmable logic. It has a NoC, a network on a chip, integrated. it will have these special hardware, software programmable engines that we haven't revealed the architecture in detail. But this is going to really provide that next factors of performance boost, and it will be something that helps build the future of the industry as we discussed. So thank you very much. Hope it gives you a flavor for our technology and the future.